Especially nice to see Ting join us from the hospital, and wish you well. Hope you have a good recovery. And always nice to see Klaus over there in Germany. All right, take care.
Yeah.
Thanks, Leon. So next is Travis. I see him there. Introduce yourself, Travis.
I'm the developer of zeptoforth, which is a forth for Cortex-M microcontrollers. The president supports the STM32F4, F7, L4, and the Raspberry Pi Pico discovery boards, and the Raspberry Pi Pico, and other compatible RP2040 based boards. It's specifically a multitasking system with priority scheduling and a whole range of useful multitasking constructs. And furthermore, on the RP2040, it supports symmetric multiprocessor. One caveat about it is it's not a specifically ANS or Forth 2012 compliant forth. It makes no attempt to follow the standards. So you'll notice that in my code examples in my slides that they are clearly following their own path in some regards. So yeah, I've been doing stuff with Forth for the last several years. And then way back when in high school, I also was working with Forth. And then I went off to the functional programming world, and then I eventually came back to Forth. So okay, I'm going to bring up my slides now. Am I showing my screen? Oh, there it comes.
We see your screen.
I see it now.
Do you see my full screen slides, or do you see just my original window?
We see your full PowerPoint with the slide index on the left and a slide that isn't occupying the whole screen in the center, and the toolbar on the right.
Okay, I'm going to have to go ahead and reshare. Now you see my first slide as a full screen.
We see symmetric multiprocessing and zeptoforth on Raspberry Pi Pico for a whole screen.
Okay. After I'm done, I'll go ahead and put in the chat the address of this presentation, because I got way too many slides as it is, so I'm probably not going to get to all of them. And it's specifically aimed at, it aims to be a RTOS with SMP support. It's a few little areas where it's not truly SMP, but for the most part, unless you try to write to Flash or you try to reboot, it's SMP. Here's a simple example program. And we'll see on the next slide what it does on the actual Raspberry Pi Pico, where here we have two different LEDs the same LED being toggled at two different rates on two different cores, with both cores being able to access the same GPIO simultaneously. So it makes an interesting pattern in how it toggles due to the toggling being at different rates and at different phases. Why isn't it showing my video? Show my video before, but oh. Video acted erratically. There it goes.
Yeah, I saw the LED blink.
Yeah, I know it. I tried to make it in OpenOffice, not OpenOffice, LibreOffice, make it loop. I couldn't find any way to make it loop properly, so it doesn't look that impressive. But and here are just some basic words: pause, MS to halt the current task for a certain number of milliseconds. User variables, which are task local variables, which are used liberally throughout the code base of zeptoforth. You can get the current number of CPUs that are supported by the microcontroller in use, the current index of the core on which the current task is operating, and the current task. You can spawn tasks with parameters and execution token, the sizes of the dictionary, data stack, and return stack, and either on the same core as the spawning task or on an arbitrary core, with the cores being on the RP2040 being either 0 or 1. And once you spawn the core, you have to run it. There's also some other routines I didn't get to it here that you can stop them or you can kill them. You know, killing them isn't always well advised because under certain conditions it can produce undefined results. And tasks are always allocated high in RAM and subtract their memory from the main task's dictionary without changing the here pointer. And here's a very simple program. It just outputs a asterisk every second. And those numbers there are the sizes of the various spaces that are allocated. They seem rather large because we have to take nested interrupts into account. And also because the dictionary space includes all the user variables, including the ones used internally. And there's priorities, where at any given time, the task with the highest priority executes. That is able to execute. That is, it's not waiting for something or it's not halted for one reason or another. And you can dynamically change the priorities as well. Furthermore, I get into this later, there's resolution of priority inversion for locks, where it uses the priority inheritance algorithm to resolve inversion. And here's a simple example where it outputs alternating sequences of asterisks and SXs because when it's the task that outputs X's is running, it has full control over the CPU aside from interrupts. And because it is of a higher priority. As we see, it has a busy loop to prevent giving up control, whereas MS always gives up control of the processor. Note that priorities operate on a per core basis, where each core has a different, where you can have one task on each core, which have different priorities, and they'll still operate as if they aren't, neither will take control from the other. They have to be on the same core, which is why we used, in this example, spawn rather than spawn on core to demonstrate this. And then there's timeouts. Because this aims to be an RTOS, all operations that block in the multitasking system can be made to timeouts, which is if they block too long and with a time specified in 100 microsecond increments, it'll stop and generate an exception. As we see here, where this will wait a second and then it will output block timed out because it's waiting to receive a message on a channel, on a rendezvous channel, and it never receives it. And now we're getting into some of the multitasking constructs that are used for communication and synchronization. A simple one is semaphores, which are basically self-explanatory. The one aspect about it that's not entirely obvious is that you can set a limit on how high the count can get for a semaphore. Or you can set no sema limit, which says no limit at all. And you can also set an initial counter as well. And you can take, the terminology here comes from free RTOS of take and give, but I've seen a number of different names used for these functions, where take goes and blocks the current task, decrements the counter, and then blocks the task until it becomes zero, until the count becomes zero, and give increments the counter, and if the task is less than or equal to zero afterwards, it unblocks the longest block task waiting on the semaphore. And here is a simple example. Again, it just outputs an asterisk every second, but it uses semaphores, in this case, a binary semaphore across multiple cores. And then a more lightweight data transfer / synchronization construct are notifications. This was also inspired by free RTOS. They differ from semaphores in which they are capable of higher performance than semaphores, and they store single cells of data in mailboxes, with up to 32 mailboxes per task, which can be updated when tasks are notified. The disadvantage of that you can't have, with a semaphore, you can have multiple tasks waiting on the semaphore simultaneously, and then you can wake up one of them. But with a notification, you can only wake up one task. And furthermore, there's no means to avoid the issue of lost wake-ups if two wake-ups occur in close succession. And here's just some of the words to implement this. And here's an example which it updates a counter every second, and it prints the counter on a task on core 0 while being notified from core 1. And locks are self-explanatory. There's not much to them. One note is that there's with lock, which is the the style-wise what I would recommend one use, because with lock, it handles exceptions properly. So if you have an exception occurring within your execution token that's called, it will unlock the lock regardless. Whereas if you use lock and unlock manually, unless you take care to make sure to unlock it if an exception occurs, you'll leave your lock locked, and it's generally undesirable. And here is an example program that it counts from 0 to 100 in one task, and from 0 to FF in hex in another task, while ensuring that the two tasks don't interfere with one another so that they don't overlap. Queue channels are simple queues containing fixed number of fixed size slots for messages that are shared between tasks. Sending to a full queue channel will block the current task until another task receives at least one message. Receiving from an empty queue channel will block the current task until at least another task sends at least one message to the queue channel. Note that you generally want very large queue channels as you possibly can if you care about bandwidth, whereas if you care about latency, you want very small queue channels.
Can we ask questions?
Sure.
Oh, okay. Andy here. I wonder, is this documentation available, written up somewhere? I know this is being recorded, so we can always play back the recording, but is there a write-up somewhere I could look at later?
It's in two places. I have these slides up on the interwebs. Once I'm done presenting, I'll paste the URL into the chat. And furthermore, there's documentation of this on the GitHub for zeptoforth.
And if you send a copy of your slides to Dave Jaffe or to me, we'll post them on the SVFIG website and put the reference in the meeting notes.
Yes, and the documentation in the zeptoforth GitHub is far more extensive than these slides. There's a lot more functionality that I'm glossing over here because, well, I simply would not have time to present it all by any means. And of course, here's the words to send and receive channels. There's other sending and receiving words I have not getting to here, which are including non-blocking modes, peaking, skipping, things of that sort. And here's a simple example which it sends and receives just incrementing numbers once every second from a task on core 1 to a task on core 0. You'll see this on my code, these words provide allot cell and extract allot cell. These are words for taking values, packaging them up in temporarily allocated data allotted from the dictionary and providing it to what's being executed so it can be something can be sent, or doing the same and extracting data and returning the value there, and afterwards decrementing the here pointer to restore it to its previous location, including with exception handling, so that if an exception occurs, it still decrements the here pointer. And you'll see that a lot in the code here. It's not specific to what I'm presenting, but it's stylistically what I use primarily for these kinds of things. Rendezvous channels, they're called F-chans because when I first designed them, they were supposed to be fast in that they didn't actually copy the data unnecessarily being sent, but it turns out that they're not really any faster in practice than Q channels, except for that you can send arbitrary blocks of data and don't have to specify a specific size ahead of time. They also do not use a queue. They're different from Q channel with element 1 because when one task is sending on a rendezvous channel, it blocks until another task receives from the rendezvous channel, and then it copies over the data, and then both tasks continue. Or vice versa. If one task is going to receive and no task is sending, it blocks until a task sends, and so on and so forth. And here's just the API calls. And here's a very similar example to the previous example, except for that as you see, no data is being allocated for the contents of the channel. If the the buffers that exist are purely within the sending and receiving tasks, the memory that they provide, with nothing being sent in between. Okay. Bidirectional channels, aka R-chans for reply channels in zeptoforth, are very much like rendezvous channels, except for they provide a means for the receiving task to reply back to the sending task, which essentially doubles the bandwidth that's possible because it allows a number of optimizations in the sending and receiving process. And if you use two F-chans to send back and forth in two directions, as you see, there's a reply R-chan word here, in addition to the send and receive R-chan words. This is used after the receiving R-chan has received. It then replies back to the sending R-chan, which then, as you see here, it provides two buffers, one for sending and one for receiving. And it returns the number of bytes received. And here's a simple code example, which is like the previous examples, but it involves a value being sent from a task on core 1 to core 0, the task on core 0 receiving from the core 1, and then immediately replying back the same value. And then the task on core 1 printing the value that it replied back to it. And streams are like Q channels, except for that they're saying there's bytes in large numbers across, which are optimized for, as opposed to sending discrete messages. And if one wants to send arbitrary sequences of bytes, I would highly recommend one use streams as opposed to receiving one byte at a time with the Q channel. And by this, it can achieve significantly higher bandwidth and lower latency than receiving individual bytes at a time off the Q channel. And here's some of the words that are used, but there's actually many words for different settings of modes of sending and receiving that are available, which can be seen in the documentation in GitHub. And here's a simple example where it sends characters across a stream from core 1 to core 0, and then it prints the data that is sent across. One thing to note about this, and I didn't explain this with Q channels either, is that it keeps on sending until it either runs out of space in the channel or stream, or it runs out of time in its current task's time slice. And likewise with receiving. With receiving, it keeps on receiving until it runs out of space. It runs out of available data, or it runs out of time in its time slice. And this is part of how it can achieve higher bandwidth than rendezvous channel, because the rendezvous channel has to block most times that it's trying to send or receive data, whereas this only blocks when it fills up the channel or stream, or empties the channel or stream. And you'll notice a little word here, with allot. With allot is another little helper word that I have, which it allocates a given amount of space on the dictionary temporarily, and then frees it up again once it returns, once the XT that's passed to it returns, including if an exception is raised, it still relinquishes the space. And that's all of the slides. Any questions?
Yeah, I have some questions.
Go
Make
ahead.
it a limited scope, Andy. Please go ahead.
Oh, yeah. Okay. So this sounds very interesting to me, but I guess I can't use this on my Raspberry Pi 3B, I gather. It's only on the lesser size of older Raspberry Pis. It's not available for more advanced Raspberry Pis?
This is for the Raspberry Pi Pico.
I read about that. So how hard would it be to carry on your ideas on a Raspberry Pi 3B? I guess that'll be a lot of development work.
And you can also use this on the STM32F4, L4, and F7 discovery boards. The only difference is that you can't use Core 1 because those boards are not multiprocessing.
Okay, well, I'll keep this in mind for some future project, but now I got to finish the one I got on the Pi 3B using G-Forth. But this is very interesting. It kind of reminds me of what I used to do over a couple of decades ago with Win32Forth. Has quite a similar capability on a PC.
Is there one last life or death question?
I'd like to, one thing, it's impressively clean. And the one thing I'd like to know is what motivates the whole, this very substantial amount of work.
Well, it was originally motivated by that I'd actually worked on a couple PC not embedded forths before I started working on zeptoforth. I always implemented multitasking. And while a lot of forths are cooperative multitasking, I initially started out with cooperative multitasking. I then was like, well, maybe I should go for preemptive multitasking. But then I was like, why don't I try to implement an RTOS, an actual RTOS, as opposed to just a bare bones multitasker? And furthermore, but then when I heard about the Raspberry Pi Pico, it's like, it seemed intriguing. I was like, at first I was originally going to go and simply use the second core for a single thread of execution. But then I was like, no, I should go and implement symmetric multiprocessing as long as I can. Note that one thing about this is that even though I've implemented symmetric multiprocessing on RP2040, if you can get it, and that's a big if because of the big chip shortage, I would highly recommend running zeptoforth on the F4 or F7 because you can get so much better performance out of it on those discovery boards than on the RP2040 due to issues with the 16K XIP QSPI flash cache on the RP2040. But it still is really neat going and actually implementing symmetric multiprocessing on a board for this. I do have a STM32H7 board, like the one that was mentioned previously, that I haven't gotten out of its packaging because I haven't thought of how to go and wrap zeptoforth around it, considering that it's an asymmetric multi-processing system as opposed to a system capable of symmetric multiprocessing.
Okay, thank you, Travis. There's a question from Saddles you might want